All right, good morning, everybody. Welcome back to the fourth day of series of lectures of our CosmoLattice school. Today we start with a practice session on playing with gravitational waves. So putting in practice a little bit the theory that Nicolas was presenting yesterday. Today Jorge is gonna lead this practice with the help of Nico. So please guys, the stage is yours.
Okay, so good morning, everybody. I hope you are having a nice week and enjoying the school. So today the plan is to have a practice session about the gravitational waves so that you can spend some time trying to play with CosmoLattice, so getting more comfortable using the code, getting to know a bit better how to use the code, and in particular how to use the gravitational wave part. So in particular, today I will present we will try to do two different exercises. First one with a lambda 5 to the 4 model, and I will present you. So I will ask you to do some small simulations, and so that we can try to solve different questions you could have, and you can. So the objective is that you manage to run some simulations, but then I will also show you some results for bigger simulations that we cannot do in real time, that you would need a cluster to simulate. Then we will do kind of the same with the model that you treated yesterday, or you worked with yesterday in the practice session. And finally, in the last part of this session, I will try to show you some other applications that we've been studying during the last couple of years, in which we have used the gravitational wave module of CosmoLattice to simulate different physical systems. So first of all, we are going to start with the lambda 5 to the 4 model, and this model is the objective now is that you try to implement this model. So this model should be very similar to the one you were viewing with Paco 2 days ago. Although now we just want to focus on the simplest example on this potential here without any daughter field, so just one single field. And here I show you which is the parameter field that I have used, and this is also what I recommend you to use. So in particular, what we are having different now than what we had with Paco is that now we are having the gravitational waves on. So we are setting this flag, the with GWs, to be true. So I think that the best option now is to give you some time so you have tried to implement this. If you have any question, or if you have not yet been able to implement the simulations, you can ask everything. Indeed, has anybody still not been able to run a simulation, even a very small one, or to compile the code?
Maybe can we rephrase the question, like those of you who have tried to compile and run a simulation but somehow failed, for whatever the reason it didn't work properly, can you raise up your electronic hand? Good. So we assume that everybody then has managed to run something.
So the exercise today now will be to try to modify what you did on the first day with Paco to go from having, so if I'm not wrong, Paco, you used two different fields. So you had this inflaton field 5 to the 4, but then it was coupled to a daughter field. So what I would like you to do here is to try to implement this simpler model, which should also run faster if you do the simulation, and then to run a small simulation with 32 points per dimension, for example, and try to see what you get. And in particular, you should be able to get something similar. So in particular, for the gravitational wave power spectrum, you should be able to get something similar to this. And I know this doesn't look very pretty. The reason is that we are working in a relatively small lattice. But first of all, let's try to get this result, and then we can discuss the physics related to it. So if any of you has any comment, any question, or any problem, just unmute yourselves and ask or write any question in the chat.
So there is a question in the chat about
So I saw
Alex saw
okay, yeah. So that's a nice question. So when you run a simulation in CosmoLattice, usually the initial conditions, by default, the initial conditions that we use are randomized. So they are random initial conditions. So this base seed parameter is indicates which is the random seed that you want to use. So you don't have to specify it, and if you don't, the program will just generate a random initial seed. But if at a later stage you want to repeat the simulation and get the exactly same results, you need to specify the seed to be the same. So the seed, this parameter allows you to repeat simulations with the same random initial conditions, so that you get the same numerical results every time. Yeah. So this is also in the CosmoLattice manual. I usually have all this in my parameter files, but it's explained in the manual that this is an option for a parameter. All the parameters that appear here should be explained in the manual. Well, the gravitational wave parameters are not in the manual because they were added in a later module.
Yeah, let me highlight or emphasize once again that good practice is to have the manual at hand, such that when you want to look for some particular wording that we are using, command, etc., if you search for it in the manual, you'll see that it's fully explained in general, unless we forgot for whatever the reason. But The idea is that in the manual, all these aspects are all explained, except for the gravitational waves, which are explained in the technical notes.
There is another question in the chat.
Okay. So the initial amplitude and moment are set in GeV, but in the code, it running the rescale program variable. Does any output relate with GeV? So the outputs are always in the rescale variables. So you can always turn them again. So you should know how. So you have already seen, like I think the first day, how the different quantities are rescaled or redefined into dimensionless variables. So everything the code outputs is in dimensionless variables, but you can always, using those rescaling that you know, you can turn them into the GeV quantities, into quantities with dimensions. So for example, the field amplitude, you will get a value which is dimensionless in the field parameter, in the scalar field dot the average of the scalar field output parameter. But you can always multiply it by f star, which is usually the initial field amplitude, to get the result in GeV.
There is another question in the chat.
Okay. Why does the peaks of GW are around omega? Always around omega star. I'm not extremely sure I understand this question.
I
So maybe I can
answer.
okay.
Oh, Nico, go ahead, of course, please.
So, well, basically, because omega star is some energy scale relevant to your problem, so it is kind of so
I understand.
whatever feature that comes in your gravitational wave spectra is related to the relevant energy scales of the phenomena, or the, let's say in this case, parametric resonance of the field. So yeah, if you choose well your omega star, that means that your phenomena is happening at those scales, and yeah, we expect that the peak of gravitational waves to be peak around our value of omega star, but that's why we choose omega star in that way. So maybe, I don't know if Danny wants to compliment. I mean,
that was perfect.
Something else.
All I could add is that goes the same for any scenario. You know that a right choice of omega star is precisely that your natural momentum units are of order 1. Because precisely the idea is that your choice of omega star is dictated by the physics of your problem. In this case, the problem is parametric resonance. And there is a given scale based on the dimensionful constants and dimensionless parameters you have in your theory. And if you understand the physics behind, then you are going to choose, an appropriate omega stars at your typical kappa, so the normalized momentum, moving momentum, in this case, it's order 1. Which is, let me repeat something that we've said, I think, a couple of times. It's not mandatory in the code, if you don't do that, if you don't choose that, the code is going to run anyway. But I think it's more convenient to make these choices because it allows you to immediately interpret what are the energy scales or the length scales in your problem in terms of your dimensionless and dimensionful parameters of your theory.
And also numerically is more convenient having everything to be order 1. Because
yes, numerical is more stable also. Yeah. This is true. Yeah. It's a good practice, honestly, and of course requires you to have a handle of the physics before you just put it in the computer. So in principle, the idea is you should never, if you just try to get the physics out of a model blindly without really understanding initially what's the expected physics going on, it's gonna be very difficult that you set up correctly your lattice simulation, because you first need to have insight, about the time scales, spatial scales, etc., from your problem. And this is what will help you to set up F star and omega star and alpha. Another question.
There is another question in the chat, yeah.
So Isaac is asking, or Isaac, what happens with the output if I decide to kill the simulation after some step? Is it still in meaningful format that can be read by the plot script? Yeah. So the output is I think always the outputs are written to the TXT files after the number of time steps you have specified in your parameter file. So in these T output frequent and T output infrequent parameters, you say after how many units of program time you want to output or to measure different quantities. So after those number of program units of program time, the quantities are saved into the output file. So you should be able to read so you get the results saved. So this means that if you stop the simulation, or if the simulation gets killed by some reason, anything which has happened before, you still get the results saved.
Okay, thank you. But I also wonder, do you also dump, let's say, the full 3D frame at some point so that you can restart the simulation?
So that's not something which is done by default, but that's something you can do. You need to specify a parameter. So you need to specify that you want to make backups. And it's as easy as saying, I want to make backups this number of steps. And you can see which is the name of the parameter in the manual.
Okay.
So the only thing that I will take into account if you do that is that if you try to run a big simulation, these backup files get very large.
I see. But are they written in binary format or?
Yeah, they're in HDF5, so in binary format, but they can get very large.
Yeah, I see. Yeah,
and they don't have, making the backups doesn't have a big impact into the simulation type. So it does, I mean, if you make backups every very few time steps, it could have an impact in the running time. But if you only make like every time units of program time, for example, or 20 or something like that, or 50 or 100, depending on the problem, there shouldn't be any effect or any overhead in the time required for the simulations.
I see. Okay. No, I'm asking because I think I have to kill my simulation at some point now, because I was setting Tmax to 2000, but now I think it takes on the order of 2000 seconds to run.
Oh, so maybe you can put 1000. I think that the figures I'm showing are in reality only up to 1000.
But that means in practice I can just kill my simulation at 1000.
Yeah. At any point you can kill your simulation, and you should be able to print it anyways.
Okay, thank you.
Yeah, in any case, I think the feature you are asking about, which is a very interesting feature of CosmoLattice, the ability of restarting the simulation from the same point, is really meant for very large simulations, not for this practice, in the sense that if you launch a gigantic simulation in a cluster that is going to take days, you don't want to take the risk if something goes wrong in the cluster, or even in your own choice of parameters, to lose whatever the data you've generated up to a given point where it could be valid. So in that point of view, it is very, very useful, the fact that these HDF5 files can be written and then reused as an input for restarting the simulation.
Yeah, I completely agree.
Yeah, actually, a typical problem, those of you, few of you that probably are already familiar with launching things in clusters, is that sometimes the time you are given to run something is very short. and then you may want to take advantage of this feature. You know.
What is the largest? So I assume you have run CosmoLattice on a supercluster at some point.
Yes, the largest we've tried so far is 65,000 cores.
65,000 cores, and what was the grid size then?
The grid size, I think we were reaching there was 4,000 something or 5,000 something.
5,000.
But that was for a scaling test.
Yeah. But I mean, the point precisely that it was scaling pretty well. You know. So.
And memory-wise, this is still no problem.
This always depends literally how many fields you have and what's the memory available per core. You know, it really depends on the circumstances of your computer or your cluster in this case, and the scenario you are running. Yes. People are launching nowadays simulations even up to 8,000 cores. 8,000 cube. Okay, 8,192 cube to be more precise, 2 to the 13. We are thinking if we are granted some time in a supercluster that we are waiting for right now, their answer to go for those scales as well. You know, in principle, the code is totally prepared to do it. The problem is to find the machine to do such a thing. You know.
But can I ask you then, what would be the science case for these kind of monster simulations for the case of CosmoLattice?
What would be what case? Sorry,
the scientific case. Like what would you like to study that requires?
Yeah, of course. I think you know, physics-wise, there are many problems where you require to separate a lot of scales as much as possible. For instance, inflation, or for instance, cosmic defect networks. Both of these problems, you need to separate the scales as much as possible, and hence as many points per dimension as possible. So what we have in mind is
okay. Yeah. But so would you say that, let's say, first order phase transitions where you couple the scalar field to the fluid would also be such a case that you have?
Well, in principle, yes, you know, because you could have much better statistics with more bubbles, you know. You could resolving separating number, so enlarging the number of points doesn't necessarily mean to enlarge the physical length scales between one point and another, because it could be about increasing the resolution of your local profiles while maintaining a good infrared coverage of your system, you know. So that could be an improvement, you know, and that includes phase transitions, of course, absolutely.
And I'm gonna show something related to that at the end.
Yeah, I believe actually a High-March group, with their fluid dynamic simulation, they are reaching already pretty sizable cases, no? In some of the examples they've run.
The largest I'm aware of is 4,200, but maybe they have done larger now.
Yeah, well, could be they haven't published yet. I don't know. You know, but yeah, I mean, I'm afraid I will discuss this tomorrow on the discussion that above 8,000 cube, it's gonna be very difficult to go above that. Maybe 10,000 cube you can do in some cases. You need so many cores, so many memory, so much memory, so much time of running, you know, etc., that it becomes a bit unfeasible. What some people have done in Berkeley, for instance, is to do adaptive mesh refinement, where, you know, the actual number of points is still, you know, of the order of what we are saying, but in practice, the simulations can be considered equivalent to a larger number of points because of the refinement they do locally, you know. But yeah, at some point, lattice is finite and you feel it. And that's a limitation that is there.
Can I also say something else? One example in which you really, even in the case that we have simulated in this school, the preheating case with a graphite to the 4, when the inflaton is coupled to one dotted field, you see that as you increase the resonance parameter Q, the separation of the scales also becomes. So there is a maximum number, a maximum Q that you can simulate. So this would be an example. I mean, for example, we could use a very, very large simulator, large box to simulate larger values of Q. So this is an example that you that you have simulated that would require a big box.
That's a very good point. Yes, thanks, Paco. You are right. For instance, Nico has simulated scenarios where, you know, there is a bunch of different dotted fields coupled to the inflaton with different coupling strengths. And in order to see all the spectroscopic signatures in the form of peaks in the gravitational wave spectrum, we needed to reach a very large scales as well, very large lattice simulations, because otherwise it's impossible to capture all the scales.
And that's also something in the presentation.
Ah, fantastic. Okay, fantastic. Sorry.
I think there is a question by Kursit.
Okay.
He has
So-
his hand.
Yes, can I ask?
Oh, yeah.
Yes. So you told me before that your code can run during inflation for last few efforts. So how many efforts it can run during inflation? Last two.
It depends the size of your box.
Okay.
And also on the scales that you want to capture.
For instance, think I take
Hmm.
1,000 points per dimension. Okay.
Mhm.
How many
Hmm.
numbers of E can I fit in the number 1,000? Okay, pues of the order of 5 E foldings. You know, E to the, I don't have a calculator right now with me.
Yeah, E to the 5 is something like
Can you do it?
300, 400 probably.
Okay, E to the 5 to the 6. So that's as more as you can do, because after that your scales will be completely redshifted out, you know, of the range of interest. This is the problem of inflation, that redshifts exponentially, quasi-exponentially.
Yes.
You know. But it's doable, you know. If so, for instance, the largest we've done is 8 fields of nonlinear dynamics matched with 8 E foldings with nonlinear dynamics with 5 E foldings of linear dynamics match. So in total 13 E foldings. And this will be presented tomorrow actually in the action inflation case, you know. And
Okay. But total around 15 efforts it can capture. Around about.
With the sizes we did, yes, which were close to 3,000 cube lattices, you know.
Yeah.
Okay, 3,000 cube lattice.
Yeah.
If I take that 4,000, then it will take it can capture more.
A bit
time.
more, yeah.
Okay.
Sorry, to be precise, it was
Thank you.
2,300 points per dimension for the 13 E-foldings, which were matching 8 E-foldings of nonlinear physics and 5 E-foldings of linear physics. Yeah.
Okay. So
That's-
when you will action, yes, sorry. Yes, sir. Go ahead.
That's about what you are gonna get with lattice simulations. You know, you can slightly increase that, but if you require to do 20 E-folds, it's not gonna happen. You know. Now, luckily, most of the inflationary scenarios do not require 20 E-folds of nonlinear physics. You know.
Okay. So and another thing, when your axionic code will be publicly available around time.
Sorry, what's the question?
Axionic inflation code, which
Action inflation code. When are we gonna make it public?
Yes.
Well, this to be seen. Hopefully next year, but to be seen. You know, because we need to exploit the phenomenology of that scenario first a little bit.
Okay. Thank you.
Problem.
Okay, so let me now, I hope some of you have been able to run one of these simulations and maybe plotted some of the results. So probably you will have found something like this. And as you can see, it seems that we are covering properly the infrared.
Jorge,
Because,
sorry.
oh, yeah.
Sorry. Can we ask them how many have managed to run this simulation? Can you raise up your electronic hand if you have managed?
To run the simulation.
Similar spectrum as this? Oh, okay, plenty of people.
Okay.
Okay, more than I can see in the line. That's really great.
Oh, that's nice. So you will probably have found some
Thank you,
some
guys.
figures, some spectra like this one. And there are two different things to comment in this spectrum. First of all, we have this decay in the infrared as is expected, which means that we are covering the infrared coverage of the simulation is nice, is acceptable. So physics are happening at the scales higher than the smaller scales at momenta higher than the smaller momenta we are covering our lattice. But then when we go to the UV, we see that there is something wrong, that our spectra is not decaying, and the reason is that we are not covering enough ultraviolet. We are having this very small lattice, so the ultraviolet is not being covered enough. So if we were to do a bigger simulation, like instead of doing 32 points, we did 64, for example, we will have a better thing. Now the peaks are being more, they are more clear there. We now cover more scales and see that after some scale, the spectra decays. But still, it seems that things are not well enough. And if we go to 128, we start to see that things just start being more smooth, and we could go to 256. We could go to even bigger lattices, and we will get better and better defined spectra. But we can see that after this point, we have more or less we are now covering the relevant scales in this model. And maybe a bit of a comment about the physics. We are what you can see is very similar to what you saw yesterday in the hyperbolic tangent model, because if you realize, and we are gonna see it later again, it is the same having both models. So it's not the same, but it's equivalent, because when if you expand the hyperbolic tangent from yesterday around the minima, you will be getting a 5^4 model. And so the peaks that were appearing yesterday in the field spectrum also appear in the gravitational wave spectrum. And these are related to the self-resonance of the field into itself. And I don't know if Nico or Danny want to add anything.
I think there is another question by Kurt.
Okay.
Yes.
What
Yes.
happened?
So you can, yes.
Yeah, go
So in spectrum plot, you are seeing lots of peaks. So why there is many peaks? Is there any reason? Because for 5^4 model, there is only one frequency is there. So why many peaks there?
These are harmonics of the main frequency, you know, the physics of parametric resonance in this case have a series
Yes.
of harmonics. And
Okay, I
there are
understand.
resonant cables at different
It represents different band of their of the.
That's right. If you want, there are Floquet
Okay.
indexes, non-zero,
Yes,
non-vanishing for different momenta.
Okay. I got it.
They become weaker and weaker as you go to higher momentum.
Yes.
That's why they fade off. A very interesting feature that Jorge was highlighting is that you see these peaks initially in the matter power spectrum, okay, in the source of these gravitational waves, but in the matter power spectrum eventually smooths out because of the nonlinear dynamics, and you remove the peaks. Whereas here, the peaks remain, okay, because once you produce them, then they propagate freely, you know, preserving the shape. So this is the idea of the very essence of gravitational wave backgrounds, that they retain the spectroscopic signatures containing the information of the source that created them in first place.
Okay, got it. Yes. Thank you.
So using this model, I'm also going to make a couple of comments about some things Nico discussed yesterday and Paco discussed on Monday, which are mainly the different projectors that we used or we presented. And this is the same model as I was showing before, but now the scale is very shifted. This is not the right scale if you want to show the physics of your model, because the physics are in the peaks, so going to 10⁻22 is not the right thing to do. But as I here want to compare between using different transverse traceless projectors, as Nico introduced them yesterday, I have to do this to properly see what's the difference. So what I'm showing here is the power spectrum from before, but now I'm comparing two different projectors. The red lines are the results using the real projector. So the lattice momentum for the transverse traceless projector is being computed using a real lattice momentum. So the transverse traceless projector is computed using a real lattice momentum, and the blue one, we are using a complex lattice momentum. And as one would expect, we have the same result in the infrared, because in the infrared, both momenta are pretty much the same. And as we go to the ultraviolet, we have started observing some differences, although the differences are pretty small. Especially if you have a box which is fine, so in which the lattice spacing is fine enough so that you cover the ultraviolet well enough. So you observe that there's some difference between using the projector. So this is this parameter here, the projector type. The 1 is the real one, and then the 2 and the 3 are complex versions. And what you can see is that in reality, there is not much difference between using one of them, or the other. The difference is mainly in the ultraviolet. And if we were to cut the spectrum, for example, if we decided to only plot up to 10 to the minus 10, then the difference is almost negligible.
But let me make a comment here, Jorge. It is true for this scenario is negligible because this scenario has a extremely well behaved behavior in the lattice, no, and that's why we are using it all the time. No, it fits pretty well the scales, has a very nice fall off in the UV, but this is not always the case. Okay, you may run into situations in where your UV coverage is borderline with being valid, and then you may see here, I'm not saying orders of magnitude, but you may be more sensitive to the choice of projector there, you know. So for instance, I remember scenarios in which the integrated energy density was changing up to 20%. Again, not a crazy change, but if you want to do accuracy parameter extraction, for instance, in the future with detection of gravitational wave backgrounds, well, these kind of details might matter, you know.
Yeah, but then the main problem is that you need to go to bigger lattices.
The main problem is what, sorry, Jorge?
That you need to go to bigger lattices.
Yeah, but you may have to live with the limitation that you cannot, no?
Yeah, this discrepancy can serve as an estimate of which are the systematic errors, the systematic effects that you are having because of putting your model into a lattice.
Yes, that's correct. And actually, as is not, I mean, I don't know if you have a zoom in version of this, but in the infrared, these projectors always coincide.
Yeah, no, in the infrared
they deviate a little bit, you know, because in the infrared, the limit to the continuum, they all flow to the same limit. In the UVs, where you feel the discreteness, no, of the lattice, as Jorge is saying.
Yeah. And you can also do a very similar exercise, but then keeping the same projector type and changing the power spectrum type. So this is more related to what Paco presented on Monday. So here what I'm doing is keeping the projector type to be the real projector, using a fixed version of the power spectrum. This is, you can see, I'm not extremely sure how much Paco discussed this on Monday, but you can read more about this in the technical notes. So what I'm comparing now is by the power spectrum in which we count the number of modes inside each beam exactly, or we use an approximation for the number of modes. And what you can see is what you would expect is that when we are in very small modes, this counting, this approximation is not very well, it's not a very good approximation. And that's because we have a very small number of modes. So then the overcounting or undercounting is more impactful. And the same happens when you go to the ultraviolet, that you start going to modes which don't, so your spheres start going out of the lattice in some points, and so the counting starts to fail again. And so you can see that these two variations lead to differences in the ultraviolet and the infrared. And the exact counting should be preferable. Yeah.
Okay, this is a very good moment, given this discussion, to bring up one aspect, which is a bit more qualitative than quantitative, but in a sense, one needs to have it in mind, which is supra-Nyquist frequencies, so modes that belong to the shells, to the spheres, as Jorge was referring to them, with radii bigger than half the length of the box of your lattice. You should take them with a grain of salt, okay? Because that's where the discretization of the lattice is becoming manifest. And all you really want is that you have a fall off of your spectrum there. The exact details are a bit difficult to tell for super Nyquist frequencies, okay? So this discrepancy in the UV between the approximate counting by solid angle in spherical cells or the SAT counting might not be so relevant after all, because the details of the tail, you have to take them with a grain of salt once again. But in the infrared, still they introduce a slight difference. And if you want to capture very well your infrared physics, or you want to capture very well your UV physics, even though you have to be careful, as I'm saying, this is where it might matter, obviously, yeah.
Yeah, the other thing about the infrared is that you can have something, since we're simulating a statistical realization of whichever model we have, the infrared has less points, and so you may run into some cosmic variance like issue.
I think there is a question by Isaac.
Is it in the chat now?
Yeah, sorry. So I just wanted to ask you, could you be slightly more precise as to how well you can trust the IR modes, and up to which frequency exactly would you stop trusting them? Like, would it be precisely at the Nyquist, or
have a look to the technical note 1 in the technical notes on our CosmoLattice website, and the precise numbers are given per bin. I don't remember on the top of my head, but
yeah, okay, but technical note 1.
Technical note 1, yeah, because it's where we introduce the difference of the different spectra, and what I can tell you is, for most applications I've done in my life, it didn't matter at all, because typically you want an infrared tail falling off to some power as close to k to the 3 as possible, as due to causality,
Yeah.
But for instance, in the case of a network of cosmic defects, where your physics is infrared all the time, and you are like tracking the Hubble scale as it gets larger and larger, the Hubble length scale, there, if you want to differentiate good enough what is your physics, well, I would do it as precise as possible, which is the exact counting. On the other hand, there is the problem that Jorge just highlighted, which is you are affected by a cosmic variance problem, which is the statistics to sample in your infrared modes is always way lower than your statistics for the more UV scales, for obvious reasons, if you understand what the lattice is.
Yeah. So in the infrared, regarding this figure, for instance, I would be more concerned, rather than being concerned about whether I'm using an exact counting or an approximate counting, I would be a bit more concerned on whether this is going to change a lot or not if I do a simulation with a different random initial condition.
Yeah. But there is a way to overtake that. Thanks for bringing up that point, Jorge, which is, if you are concerned about that, you can run 10 different simulations, the same simulation with different seeds, so that you generate different realization of your initial random fluctuations. And then you take the mean value of all that. So that way you are increasing your statistics in the infrared. However, whether you are exactly counting or not exactly counting can affect the shape, and that's why if you have a system which is infrared sensitive, as it is the case of a network of cosmic defects, you may want to do this kind of exercises.
So ideally, you would like to have a simulation in which all the physics happen in intermediate scales, and then both the ultraviolet and the infrared, which are affected by these lattice artifacts, are not relevant for the physics. But that's not usually possible, because
that's very often possible, thanks God. But
you want to go.
In some cases we cannot, or in some physics scenarios.
So the more greedy you get with your physics and your scientific basis, the more difficult it is to actually separate the scales properly.
Actually, I wanted to bring one case, sorry, that I think was not properly discussed before. Paco, are you still there? No. Okay, well, we wait for him.
Yes, I'm here. Sorry.
Okay, go ahead, Paco, sorry.
Okay, sorry. So related to this previous issue of trying to simulate preheating lambda 5 to the 4 or hyperbolic tangent to the 4 potential with a single Doppler field. yeah, I wanted just to explain this a bit more. There is like as you increase the number Q, right? The scales, the infrared scales that are excited initially, and then the later scales that get excited later, right? The separation between these two scales grow with Q. And I think in 2017 we parameterized the separation, and it grows a power law of Q to the alpha, where alpha is one number, which is around 0.4. So this means that given a lattice at the size of a lattice box, then there is like a maximum value of Q that you can really simulate in the lattice. You want to cover both in the initial linear and nonlinear regimes. So for example, I mean, you can test that in the simulations that you've done. You change the Q, you increase the Q, and there will be a point in which the spectra go escape the lattice, no? Go too much to ultraviolet, and then you cannot process simulations. So I think for example, for 256 points, if I don't remember correctly, the maximum Q that you can simulate is 5,000. So if you want to go to 10,000, you will need a lattice of 512 points. So I think this is a natural scenario that you have practiced and in which you can see. I mean, you can play with them. You can see how the number of points limits you to simulate certain scenarios. And you can play with it because you already have the model. So yeah, I just wanted to say that.
Thanks. Guys, one comment to Jorge. We've been over 45 minutes. Do you want to 5 minutes break, or you want to?
Oh, yeah, maybe we can take a break. So I'm gonna, yeah, we can take a break, maybe.
Official break, officially stated from now on.
If you have any questions, we can keep discussing them.
Sure. I throw a question to the audience. You may have noticed that we have a tendency in all the practice sessions to show you 5 to the 4th, times to the 4th. So my question to all of you is why 4 and not 2 or something else? Understanding that we can do 2 or something else or many other scenarios, okay? But there is a reason why we are cherry picking this 4th power, you know, and that's what I'm asking about.
So you have a question, an answer done in the chat. So maybe we can continue now. So the next thing I wanted to cover today was the models you treated yesterday with Nico. So the hyperbolic tangent models. Since it's been a bit more time than I was expecting, I'm just gonna briefly comment about this first case. So the model you were working with yesterday was this hyperbolic tangent to the fourth power. And I'm pretty sure this should be a 2 rather than a 4. No, this is fine. So this was the model you were seeing yesterday with Nico. And if you wanted just to simulate the gravitational waves, it's very easy. You just get the same model you were using yesterday, and you set the gravitational wave flag to true, and you can make the simulation. It's exactly the same as yesterday. The only things you have to take into account when running, again, as to make sure it's clear, when you run a simulation with gravitational waves, it runs slower because you are simulating the gravitational waves. So in these gravitational waves, as you saw with Nico, they are simulated as 6 additional scalar fields or effect like scalar-like fields. And that takes time. And also it takes memory. So if you are planning to run a very big simulation, you need to take that into account for estimating the memory budget. But for this particular model, as you can see, if you approximate it around the minima, it's going to be very similar to the model before. So what you are going to get is a very similar result for the power spectrum, which is, so this is almost the same we had before, and you can do the same exercise and go from 32 points to 64 points. You get better resolution in the ultraviolet, and you see a better resolution of the peaks, 228, and you can, so I here have an even 256 simulation. These were done by Nico. And what you can see is that as you improve the ultraviolet resolution, you capture better the scales in your simulation, and so you improve the results of your simulations. And here, for example, what I'm representing, or with what we are representing, is the last spectrum measured in the previous simulations. Although I don't, so here the black line is the 32 point simulation. The green one is the 64. The blue one is the 128, and then the red one is the 256 simulation. And what you can see is that there is some kind of convergence, especially in the infrared. There is some convergence. We are not yet in the convergence region in the infrared, but I expect that if we went,
in the UV, you mean?
I said in the UV. So the infrared is pretty much convergent. So up to here, the 128 and the 256 are almost on top of each other. And the differences are probably just related to statistical differences. Because that's another point. It's very hard, in principle, to run the exact same simulation in the statistical meaning, so with the same random initial conditions for simulations of different sizes. Because when you initialize one simulation, you random initialize all the points. So if you have more points, the initial conditions are going to be initialized in a different manner. You can do some tricks, but it's not straightforward. So, but what I would expect here is that if you went to a 500 cube simulation, then things were start converging more and more in the ultraviolet. The interesting thing here that I think you should try is to run the gravitational wave simulation with a Doppler field. And for example, here I think you also saw yesterday this with Nico. And then what I'm asking is that you try to add a Doppler field and try to get the spectrum. And maybe I can give you some time for you to try and do this.
Jorge, sorry, just to understand, this omega star is just for p = 4, or
Oh, so this is CP4, yeah. Sorry. This is a typo in the slide. Yeah, these quantities here are meant to be for a p equal to 4. Yeah, we'll make a comment about the general P later.
So I think maybe if you do this simulation with the 32 points, you can just go as much as 500 in the maximum time. I think it will be enough.
Oh, yeah.
For this choice of resonance parameter. So, and you can even choose a slightly larger DT. It will work as well. So just you want to get the simulation done in
So
less
you
time.
think something like 5 is
Yeah, you can
is-
have 0.5. It will be fine too. Yeah, because I was doing that just now, just to check.
Okay. So this is gonna be much faster. We try to do this. But the main thing you have to notice is that there is no, the difficulty of running gravitational waves for your model is close to 0. You just have to set the flag to true, and you can run the gravitational waves in the linear regime.
Sorry, why in the linear regime, Jorge?
I mean, because you are not, so the gravitational waves we are simulating are, we are in the linear regime of gravitational waves. I mean, this
Okay.
means that we are not considering back reaction or
You-
anything like that.
You mean in this example? Okay, sorry, yeah. In this particular.
No, I meant in CosmoLattice, the gravitational waves. Yeah, it's not the linear regime. How do you call it?
No, sorry. I mean, so
The
don't call that the linear regime, okay?
Okay.
Because that's very confusing.
That's confusing.
Yeah.
Oh, so
Let me explain what.
yeah, I just want to make clear that we are not simulating gravity. We are simulating the linearized gravity in some sense.
Yeah, what we are not simulating is the back reaction of gravitational degrees of freedom into the matter field dynamics, okay? Because typically the gravitational degrees of freedom, which are gravitational waves, are very, very small perturbations, and their back reaction is negligible into the matter fields, okay? So in that sense, we are simulating gravity in a passive manner. Like we take the source, which is the dynamics of the scalar fields, gauge fields, whatever you have, and then we obtain the gravitational wave background, okay? But there is no back reaction of that background into the expansion of the universe or the matter fields, matter field dynamics. But let's not call that linear regime because it's never like that.
Sorry for
I don't know, it's just not a common terminology, okay? Passive, I think passive use of gravity is more common.
Okay. Yeah, I just wanted to make sure that you are sure or not, you have clear that CosmoLattice does not simulate back reaction of the gravitational waves into the matter fields, and it does not simulate a gravity or a strong gravitational regimes.
On the other hand, people with full GR code have simulated these scenarios as well.
Yeah.
And the outcome is pretty much the same. Okay, so linearized gravity, or absence of back reaction of gravitational perturbations on the matter field dynamics is a very, very, very good approximation.
Yeah. So maybe I can move on and show the result of these simulations. So this is the power spectrum of gravitational waves when you work with 256 points. And as you can see now, the addition of the daughter field has completely changed the shape of the spectrum. And now we are getting this much smoother spectrum with a maximum. It's not. How do you call it?
A peak, you mean, or
A peak? Yeah, I know you also use another word sometimes, but
bump?
bump. Yeah, bump.
Well, bump or hunchback, something like that.
Hunchback. Yeah, hunchback is also another word we use. So there is a bump around 5, I would say here. And what you can find is that indeed the position of this bump varies as you vary the strength of the coupling to the field, to the daughter field. And this is something that Danny and Nico and Adrian exploited in a work last year. I think it was last year, where
Yeah,
they studied
it was.
how by measuring the gravitational wave background by measuring gravitational wave background, one should be able to determine these couplings, even in the case in which there are multiple daughter field species. And this is something I'm gonna show a bit later.
I think there is a question by Kursi.
Okay.
So, in this spectrum, you are not seeing as many peaks like 5 to the power 4 model. So why you are not seeing many peaks in this
Okay,
case?
so this is because now we have a adapter field coupled to the infleton through that coupling.
Yes.
And usually let's say the parametric resonance of this adapter field with that coupling strength, or in this case the resonance parameter being 100, is much stronger than the self coupling of the infleton with itself. So the initial instability band of the parametric resonance of the adapter field is the one that will first create the gravitational waves, and because it happens for a broader band, it doesn't happen for these small windows that in the case of the 5 to the 4 alone. That's why it creates this feature without the peaks. So it's because the adapter field back reacts first than what it does the inflaton. So that basically the peaks are lows here.
Because daughter field has a showing baud resonance. That's why.
Yeah, the adapter field back reacts first, and the adapter field is created first. Let's say it resonates. So parametric resonance happens
It resonates
first.
faster than the daughter field. It resonates faster than the inflaton. And
well, faster in the sense that it happens first.
Yeah, yes, it's happened first. Yes.
Yes.
So
Yeah,
and this daughter field showing the broad resonance. That's why you are saying you are not seeing as many peaks at 5 to the power 4.
Well, so here, in principle, I think you can choose a resonance parameter such that it creates also a peak structure, but then the nonlinearities will usually tend to, well, no, this I don't know. I think if you choose a proper resonance parameter, you will also have these peaks. But in general, the common kind of spectrum that you expect are these kind of flat spectra with some peak around certain scale to the UV. So when you increase the resonance parameter, your hunchback or your bump will be more towards the UV. That's the general shape of the spectrum you expect from these cases.
Yes, if you change your if you increase your Q, then your peak of the spectrum will move to the larger K. But
Yes,
I'm not asking this question. I am asking why you are not seeing the many peaks for 5 to the power 4 model. You are seeing the many peaks, multiple peaks, but here you are not seeing the multiple peaks. This is my question.
That these are being hidden now. I mean, these are being hidden in the spectra because I mean they were produced, but the gravitational waves produced by the resonance parameter of the adapter field are larger in this case. But if you choose especially for the 5 to the 4 case, a Q, a resonance parameter that creates a feature for a very, very long case, you will see that the peaks of the 5 along will remain there together with this additional peak to the UV. That's something that we have checked, and I don't know.
If I go to the larger
I think in the
value,
paper there is
you
this
can
paper of the by Danny and Paco where you can see those kind of
in this
spectra.
plot, yes, in the before plot, if you see the
In this plot, you cannot see
there is a
because the
multiple
resonance
peaks.
parameter
No,
is
no.
not large enough. That's the reason. If you choose a resonance parameter large enough, you will see that there is a bump to the larger case, K values, and then there is the peaks of the self.
So you get something which is like this, then you have a peak.
Yeah, something like that. You have
And
peak,
then-
peak, and then towards the UV you will have a bump.
So why,
But yeah,
no,
the
no.
peaks are there, but in this
Here,
case are hidden.
so here you are seeing the only one peak, or only one peak. But if you see 5 to the 4 model, there is a lots of peak. I am saying it can go to the 5 to the 4 plot. This plot. If you say this plot, in this plot you can see that there is a multiple peaks. And
Yeah, so you can notice the scale. So here you have the peaks are around 10, they get to the highest one gets to 10 to the minus 5.
10 to the minus 5, yes.
In the other figure, everything is around 10 to the minus 5. So
Minus
what is
5, yes.
happening is that the self-resonance, so the Q parameter here is big enough such that the dominant physics come from the interaction between the two fields rather than from the self-interaction of the inflaton field into itself. So you are getting that these multiple peaks are getting like superseded by the physics coming from the interaction.
Okay.
So
Okay.
so what you can think is that the energy of the inflaton is getting transmitted to the daughter field and then back and forth between the daughter and the inflaton much faster than the inflaton is oscillating around the minimum without transferring energy. So the physics, what the mechanism that dominates the emission of gravitational waves is another one. And this depends a lot on the value of Q. So depending on which Q you choose, you get a different final result. And
Yes.
I know that Paco and Danny, they have a couple of papers discussing this.
Yes, I have read this. I have read this paper before. Yes, I have seen this paper. Okay, thank you.
So if you have had the chance of simulating this, I don't know if you manage, but since we are running short on time, I just want to go on a bit. There were a couple more things I wanted to discuss today. The first one is I wanted to suggest that you try to implement this more complicated model in which rather than having a force power, you try to implement a model with a generic P power. And since we don't have a lot of time, I will just briefly discuss how you do this particular model, and I will just say you that this model is the reason why, for instance, we choose these different quantities. So for this particular model, it's convenient to use this omega star and this alpha. And the reason is because this is related to the typical frequency of the inflaton around the minima in this model. And you can see this in the review. In the art, it's discussed in section 8. The thing I really wanted to discuss with this model is which do you think is the best way of implementing this P parameter here? And I'll allow you to think for maybe half a minute or something like that. So you have CosmoLattice and you want to implement this model. How do you do this? So you could think of doing this in two ways. First of all, you can think, okay, my P is a parameter So what I'm gonna do is treat P as if it was lambda or if it was M, and then get it from the parameter file. So like I'm doing here. So change my model so that P becomes a parameter. And for example, this would mean that I would do something like this in my parameter. I would have that the P value is read from the parameter file. So you add it into the parameter file and you read it. So that would be one option. The other option would be doing something different, and rather than reading the parameter from the parameter file, we could hard code the P value inside of our code. So we write the model and then write the model for a particular P. Which is the advantage and the disadvantage of each of these options? The first advantage, so each of them has like one different advantage, but I think that one's better than the other. So doing the implementation with a parameter rather than using a hard-coded constant means that it's very easy to change the result. So if instead of using 4, I want to do a model with 2, I could just change my parameter and write 2. Then I want to do a simulation with 5.1, and I can do the simulation with 5.1. Then I want to do my simulation. Well, maybe with 5.1, you need to think a bit whether the model makes physical sense. But you could do the simulation with any quantity you want. If you want to do it with 6, so you just change your parameter to put a 6, and you don't have to compile again the code. You just compile it once, and since the P is a parameter, you can just change its value and run the simulations. The problem is that as you try to do, imagine you got this and you try to do the simulation with P equal to 4. What you will find is that the simulation is slower than the one you were running before, than this simulation we were doing before. Why is the simulation slower? And the simulation is slower because when we were hard coding, or if we were to hard code P equals to 4, we will be getting the code will be, and then compiling the code will be better optimized for making the computations. This means that doing, for example, doing powers like this, writing the potential like the power of the tangent to this number, where this number is a double, takes much more time than writing things like this, where we write the things as using this slightly different function where the power now is an integer. And this is just an algorithmic thing. So this second option, in which we hard code the particular exponent, is better for the runtime of our simulations. So my particular advice in this case, if you try to use CosmoLattice, is that the second option is better, because CosmoLattice does not take a lot of time to compile, but it runs much faster if you write the model in the simplest way possible, or in the more complete way possible, rather than leaving all the parameters possible as parameters. So, but I really recommend you to try to do both possibilities, and then to run both of them and to see how each of them is different, or takes a different amount of time. So let me know if you have any questions, but in the last 10 minutes, I would like to show you a couple of practical examples, of actual research in which we have used this gravitational wave module. and some things which I've been discussing in the last hour and 15 minutes have appeared. So the first example, and maybe Nico wants to make more comments now because it's his paper. Nico, Danny, or Adrian.
Yep.
Yeah.
Yeah, sure. I mean, so okay, a little bit of what we did here. So we were exploring the way of using the information that the gravitational wave background give us in order to measure or determine the coupling strengths of different particle species with the inflaton. So in this case, this is one of the nicest plots we have. What I did first was, as we showed today, with the simulations we were doing today, I just ran several simulations of the inflaton plus the after field. In this case, we choose to use the power 2 for the hyperbolic tangent potential. And I ran several simulations with just a single Doppler field and different strengths, coupling strengths or resonance parameters. So you can see the values above. We have the 3 different simulations for the single Doppler fields. On the bottom of the plot, you can see in green, blue, and purple. And then what I did was, what if I do the same simulation, but now with all the 3 Doppler fields together? And that's what happens. You get the red one, and you get 3 different peaks in the gravitational wave spectrum coinciding with the peak position of the single Doppler field spectrum. So that means that if we know by the single Doppler field simulations which peak position determines due to the resonance parameter, then we can measure the multi-peak spectra, and just by measuring the peak position, determining the coupling strength. And basically that was the whole idea of the paper. So yeah, this is a very nice application. That simulation took a lot to do, especially because you can see we're separating scales by almost 3 orders of magnitude. I need to simulate 3 like there are 4 different fields plus the gravitational waves, so it's like 10 fields. This is like a 750 grids, points per grid simulation. So yeah, this one took a lot, but you can do it. So yeah,
So can I
you can
ask
go
a question?
ahead.
Yeah.
Sure.
Can I ask a question? Yes.
Yeah.
So
Sure.
if you see the plot, violet plot, okay, you are seeing the peak around 10. So
Yeah.
what is the peak? Why this peak is appear? Here, see this peak.
Yeah, I think this peak is due to the initial resonance, parametric resonance of
Because this is a
each
tan
of the
hyperbolic
Doppler fields.
potential.
This is
So this is
the
a tan hyperbolic
hyperbolic potential,
potential.
but with the power 2, not with
Power
the
2.
power
So
4.
power 2, this potential does not show any self resonance. So why are saying this one feature then?
It's due to the initial resonance band of the parametric resonance.
So with the
So
power
the Doppler field, the one with the Q3 equal to 1.3 10 to the 7, this has an initial resonance band, and this will create gravitational waves as well. But then due to the nonlinearities, this is going towards the UV, but this is a feature of the initial resonance band.
You are saying this band is happening because of this fast resonant band.
The first initial, the first like the during parametric resonance, let's say the linear regime of the particle production. Yes.
Yeah.
Okay.
Yeah.
Okay.
So I think
So let me now finalize with the last model. So in this case, this is something I have studied with Danny and other people. And in this project, what we studied were the cosmic streams. So these cosmic effects
I think
that
there is another question.
Oh, was
Maybe
there
if
another
we went to the previous.
Oh, see, yeah. Go on,
Danilo.
Antonio. Antonino.
Yes, about this. I'm curious about the blue part of the plot. It seems a scale invariant for low K. Can you comment on this?
Well, scaling invariant.
Seems constant.
Well, it's not really constant. I mean, so in order to determine the peak,
Yeah.
what I do is usually zoom in the part of the where I put the dash line, and you can see that there is a bump there around this scale. So it seems flat because the way we plot it, but there is a certain so there is an increase of power that then peaks at the dash line.
Okay.
I think that if you capture the lower K, then you can see this
let me comment on this. Sorry, 1 second. Can you hear me? Sorry, because somehow I'm not hearing now anybody.
Yeah, we can hear you.
Yeah, we can hear you.
Sorry. I thought something
He
happened.
somehow just.
Yeah, Antonino. So the fact that it's kind of flat, around 1 decade there is just a coincidence because of the choice of the coupling, okay, that Nico took. So there is the infrared peak that you see around 20, which is the self-resonance, most infrared peak of the self-resonance of the inflaton. And then there is the hunchback peaks, that Nico got separating with the preheat fields. And in the blue case, they are not so separated away, so it's kind of flat. Look, however, in the purple, when they are more separated away, how the spectrum is falling off until it rises up for the hunchback. So there would be K⁻³ infrared scaling is more to the left of the self-resonance peak that we are not capturing because we want to focus on capturing the ultraviolet here. So you see, the more you separate the resonance parameter of the Doppler field, the more you are going to see a fall off between the self-resonance peak at 20-ish or so and the hunchback of the new resonance parameter of the Doppler field.
So can I ask a question? So for tan hyperbolic square potential, how this will self-resonate?
I'm sorry.
Because this is a m square phi square potential, how it is self-resonant? Then
sorry, what's the question? What's the question?
Yes. My question is that this is a tan hyperbolic potential, okay? Square potential. So square potential has not any self-resonant features. Has no.
Sorry. This is a square potential, not a fourth potential.
Yeah.
So how you are saying this peak around 20 has appeared due to the self-resonance? So how?
Yeah, no, my bad, because I thought we were in the quartic case. Sorry, my bad.
Yes. That's why I was asking why this peak is appear.
Sorry, then I'm not sure why that peak is there.
What I say is the initial resonance band. Is basically the
single.
Okay,
sí,
that's the initial
due to the initial resonance bands due to parametric resonance in the linear regime.
Okay, and then shifts to the right. Okay,
and then it's shifted due to the nonlinearities. Yes.
Thanks, Nico.
Sorry. Yes. I think it could be the answer when I yes.
Sorry, I was confused because I didn't see this was the quadratic. On the other hand, if it was the quartic, you would see something similar.
Then it could be, yes.
Maybe more pronounced, the self-resonance peak,
yes.
But there would be the same idea, But what I wanted to highlight here to the question of Antonino is that whether it's flat or non-flat in between is because here there are two scales in the game, which is, in this case, is the linear resonant scale and then the hunchback due to non-linearities. But if you wanted to see the K⁻³, you would need to go way more to the infrared. And this is what we capture here, with the...
Yes.
We want to focus on the UV.
Yeah. Yes.
Okay, thank you.
Yeah. So the other case I wanted to discuss is another work in which we have studied cosmic streams. And in particular, we have studied, so Danny was mentioning before that when you study networks of cosmic strings, you have this problem that you cannot capture all the infrareds because strings can be arbitrarily large, and so you cannot be larger than the strings. But in this work, we have studied single loops, like the one I'm showing in this figure. And so it's possible to have a box which is much bigger than the loop. And so it's possible to capture all the scales. But the problem is that that's also very difficult because loops are large and you need to go to very, very large boxes to properly capture the loops. So here, for example, I show the spectrum in this case, which has decays in the infrared when you go to big enough boxes, and it also decays in the ultraviolet until, so this figure is cut at around 1, but you can go to, I will later show, the next slide has a bigger box, and so you see that after some point it decays exponentially. So, and a very interesting thing in this work is that when you study cosmic defects like these streams, you have two very different scales. There is the I would say infrared scale, that is the scale related to the size of a loop, and then there is an ultraviolet scale which is related to the radius of the loop. Since the loops are field theory objects, they have a loop, they have a width, and that one determines an ultraviolet scale. So this figure here, I'm mainly focusing in the infrared part of the spectrum because that one is the one that contains the most information. But you can also go to the infrared, to the ultraviolet. So here, as you can see, the infrared coverage for these simulations was not that big, was not good enough, so we didn't see the decay. But what we saw is that when you go to ultraviolet scales that are bigger than or that are smaller than the radius, there is no more emission. So, however, we also saw that if this scale was not properly resolved, so if the lattice spacing was too coarse, the power spectrum had these unphysical peaks in this region. So we observed that only when you go to very, very small lattice spacing, you properly recover the correct ultraviolet. But on the other hand, you also need to go to bigger lattices to properly capture the infrared. And this is what I show in this other figure. So don't worry too much about these labels. It just means that as this number is bigger, this means that the box is bigger compared to the size of the loop. So for the smaller boxes we consider is the red one, and we observe that as we go to bigger boxes, like to the red one, from the red one to the orange, to the yellow, to the green, to the blue, then the spectra started to capture the infrared part of the spectrum and also got a more defined shape. So this is mainly to highlight that you need to be aware of the physical problem you are simulating, because you need to know which are the scales that you want to simulate, and you need to think which are the sizes of the boxes you need to, or the lattices you need to use in order to properly capture the scales. And often you also need to find a balance between bigger boxes or capturing the ultraviolet and capturing the infrared. So I know this is not very easy to see, but you can compare the blue here to the red here, and there is a clear difference. So what we found is that in the end we did some balance. We went for the oranges, for the orange sizes of lattices, and for something around the green here, because it's very nice to resolve the ultraviolet and the infrared, but it's not possible to do everything together and also go for big streams. So we needed to go for to make some trade-off. So this was just to show you that you can use these techniques or this module of gravitational waves to simulate physically relevant systems, and that this has already been done, and that you can also do this. And the main message you have to take home today is that if you learn to use CosmoLattice for scalar fields or for gauge fields, you can use CosmoLattice to compute the gravitational wave emission from your model just by setting the flag to be equal to true. And the second message that you should take is that this is not a complete black box. You don't just write the model and make the simulation. You need to think to plan the simulations in advance, to think which are the scales of my model, which are the ways that the scales that I'm gonna use to write my model in dimensionless quantities, which are the sizes of the lattices I need. Those are questions that you need to answer before going for the actual simulations.
And of course, there can be trial and error in guessing
those
aspects, but as Jorge said, you need to do some pre-thinking, not just to go blindly, because it's not going to work.
And especially if at any point you try to go to very large simulations, the best thing is to do smaller ones first, to try to understand the physics and to get into to make sure that your analytical pre-thinking and your small simulations agree in your expectation, and then you move to bigger simulations once you understand what you are doing, because it's better to lose or to do wrong simulations of a small size than to do wrong simulations of a big size, because of the computational resources it takes, which are sometimes not that easy to get.
Excellent. Jorge, we are over time, so shall we take coffee break here? Of course, we can remain for questions, but yeah, let's say we are officially in coffee break. We reconvene in 25 minutes. Well, see you later. Those of you who want to take the break, but we stay here in case somebody wants to take more questions. And actually, there is a question apparently already.
Okay.
Please.
So, can I ask you a question?
Yeah, of course. Go on.
So, for the gravitational waves, so right-hand side of this energy momentum tensor, basically, in the equation of gravitational waves, the right-hand side solves. Right-hand side basically the model-dependent factor, right? And left-hand side is the perturbation of the gravity, right?
Yeah, so the right hand side is the one that contains the matter fields, the matter content.
Exactly. Yeah. So that is the model dependent term. Right.
So it's model dependent, but just in the number of fields that it contains. So it does not depend on the potential, for instance. It just depends on whether you have 1, 2, or 3 scalar fields, for example. But the form it takes is the same for any model of scalar fields or for any model of gauge fields.
Okay, so if you want to add some terms in the left hand side, okay.
Yeah.
So how to do that?
So if you wanted to do that in CosmoLattice, to add something into the equations of motion, the first thing you will have to do is to think how the equations of motion are written into the evolver. For example, usually what we do are these leapfrog and these velocity varlets that we were discussing on Monday and Tuesday. So you have this conjugate momentum, and then you have a kernel to evolve the conjugate momentum. So in CosmoLattice, these kernels are in. So let me show it. So in CosmoLattice, what you have is. So this is CosmoLattice. You enter into CosmoLattice, you have the include, and then in the include, so you have CosmoLattice, sorry. Then you have the source, which contains all the relevant files. In the include, there are 2 parts, the template and the Cosmo interface. The template has like black boxes, so I think it's something in which most of the times you won't need to go in. So it contains things about the parallelization, the definition of the lattice, how memory is arranged, how the power spectrum are computed, how the Fourier transforms are performed, how operations are done, and all those things. And the relevant part is in this Cosmo interface folder. these files here are like the main files that run the simulation. But since you want to modify something about the equations of motion, you will have to go into the evolvers. Then the evolvers have all these files here. They are mainly so they are kind of duplicated for leapfrog and for velocity verlet or position verlet. So not for position verlet. Position verlet is not public, it seems. But for example, if you go into the leapfrog, and what you will find is that the scalar field, for example, or the gravitational waves, you are evolved, as we were mentioning yesterday, using a kick, then a drift. So using a kick and then a drift, because we are in the leapfrog. So just 2 steps per iteration. Then these kicks and drifts are defined a bit below in the same file. So you have the kicks and the drifts. But the main part of the drift is pretty straightforward. And the kick, which is here, is the one that has the kernels. So it's just the kernel. And these kernels are defined inside this folder, kernels. So probably what you will want to modify is the kernel here.
Let me just add that tomorrow we are going to cover a little bit the structure of the code in terms of these 3 folders. So no, thanks for anticipating, Jorge.
Yeah, I was not sure if that was going to happen.
Of course, well done. But in any case, I have another answer to this question, which is if you want to modify code at this level, you first need to understand what the current code does. Okay, and in order to do that, I'm afraid the lectures we are providing is mostly about the theory of what lattice does, or what the lattice field theory techniques really represent. But then you really need to study what the code, how the code is implementing all this. And for that, you need to go into the manual. And through the manual, you are going to have a guidance of where all these folders are, the structure of the folders, where all the different parts of the physics are implemented. And if you understand how they implement it, I'm sure you'll be able by yourself to know how to modify to adapt, for instance, a different term in the left-hand side, you know.
Yeah, so to complement what Danny said, it's in section 6 of the manual. You have a kind of an explanation of the main files that enter into the simulation. Gravitational waves are not covered in the manual because they were added at a later stage into the code. But they are pretty much parallel to the scalar fields. So if you understand how scalar fields are done, you will, or evolve, you will understand how the effective fields for the gravitational waves are also evolved. The only difference is that then you project to the transless stressless part, but that's covered in the technical notes.
Yeah, thanks. I got it.
So I will stop sharing now. So again, thank you all for attending the lecture. If you have any further question, feel free to reach me in Slack or Danny or Nico or whoever, or by email. And yeah, that's the next one is in